Thanks for watching the Real Solar Cars channel. Today's engineering lesson is about contactors and how they relate to solar charging an electric vehicle. So here is a simplified schematic diagram of an electric vehicle. It has separate positive and negative contactors, as well as a pre-charge contactor. So pre-charging will be another video. But it has the separate positive and negative contactors to operate as a double pole switch to make sure that no high voltage is able to leave the battery box unless it is specifically desired. And then that you'll just have to bear with me that my pointer is not moving on this OBS capture, unfortunately. But you can see that the high voltage goes from the battery through the positive and negative contactors and then into the motor and inverter circuit. And like I said, this is a simplified schematic. So, and there's also other high voltage devices like the heater and air conditioning compressor that are also connected in parallel with the inverter. So perhaps we could just connect our high voltage solar charger in parallel with the inverter like all of the other high voltage devices. And there are some issues with that we can discuss later, but we'll just do some math about that right now. So we found that the contactors for the Chevy Volt have a coil resistance of 35 ohms. So, and given the voltage that the car operates at, now the coils need 12 volts nominal to operate. So here if we assume 13.8 volts, actual voltage 35 ohms, we calculate Ohm's law and find almost 0.4 amps, and then we can calculate the power, which is amps times volts, and we find that it's almost 5.5 watts to run one contactor. And because there are separate positive and negative contactors on the battery pack, we need to engage both of them in order to get high voltage power in or out of the battery. So that is a moderate amount of energy loss here. Now remember that the purpose of the battery box and contactors is to contain the high voltage when it is not desired. So since we are mostly interested in charging the battery, we have if there was a one-way valve for electricity, then that would allow the electricity to go into the battery box but not allow it to come out, which could be dangerous in some situations. And there is a one-way valve for electricity, and it's called a diode. Or if you look at the schematic symbol of a diode, I know that's pretty small on here, but it looks similar to a funnel. And that's a great analogy, that the electricity can come in through the large end of the funnel and then out through the narrow end. But if you try to run water through the funnel backwards through the narrow end to come out the wider end or so, it's a lot more difficult. So here we use a diode to prevent high voltage power from leaving the battery box, but it will allow our charging power to go into it. And then of course we need some fuses, and like we had separate positive and negative contactors, we will also want to have separate positive and negative diodes. And a consideration being that the negative diode needs to be oriented at the correct direction to allow the negative current to flow. And of course we are also interested in how much energy is lost in this setup. So the diodes are not perfect, and it's typical that to have when the current is flowing through the diode, or so the diode will cause it to lose about 0.7 volts. So then here we kind of calculate off as kind of a worst case scenario. Full power from the solar array, which is about 300 watts for our 420 watt array. And to calculate worst case, we assume the battery voltage is at the very low end or so of being almost completely depleted. And we find that we are charging at almost 1 amp. So almost 1 amp times 0.7 volts is almost 0.7 watts. Worst case for one diode. Now, of course, since we'll have two diodes, that will double to a little over 1.3 watts. But what's interesting here is that because it's a constant voltage lost, that then the power lost is proportional to the current. And we find that by having these diodes here, the diodes would cause the loss of about 0.5% of the energy we are applying to charge the high voltage battery. So what if we got rid of those diodes? Again, we don't recommend this or so because it will allow you could be allowing the high voltage power to exit your vehicle's battery box. Or you could avoid that by putting the high voltage DC to DC charger inside the battery box. But that is also a bad idea because it does generate heat, and you don't want to add extra heat to your battery box. But what happens now is that since the charger is connected to the battery all the time, it will be draining power continuously, even when the charger is not charging. So to kind of calculate worst case scenario, we use a high battery voltage of 393 volts, which is almost completely charged. And then we know that the charger has an output resistance of about 5 megohms. And that is to ensure, like, when the charger is powered off, that the capacitors in there do not retain high voltage. And it's also due to the circuitry needed to sense the high voltage output, that the high voltage output has to be measured in order for it to be regulated to the desired voltage to prevent your battery from overcharging and stuff. So in here we find, calculating that with Ohm's law again, 393 volts divided by 5 megohms, we find 78 microamps, and then we can calculate the power. That is 0.31 watts or 31 milliwatts. Now the thing is, that is a continuous power drain even during the nighttime. So we can calculate that out. That is a little less than 1 watt hour per day lost if the charger were to be connected directly to your high voltage battery. And then also keeping with the theme of trying to calculate worst case scenario, we'll assume a very low value of 1 kilowatt hour from the solar array. We find that that is 0.074% of the energy lost here. So that is a lot less than the 0.5% from the diodes, but again, we still don't recommend this, and 0.5% is still not that big of a deal. But there's also some other things we can do. The contactors, even though they are designed to operate off of 12 volts nominal, they don't really need 12 volts to operate. So we in some experiments we've done, we found that the contactors in the Chevy Volt can close at only 5.5 volts. But then after they have closed, they will stay closed with as little as 2 volts. So if we had a smart contactor driver, we could supply 12 volts to them for a short while to make sure that they are closed. And then once they are closed, we could reduce the power supplied to them down to perhaps 3.4 volts. So that will still give us a good amount of margin above the 2 volts that we measured as the minimum. So then the same 35 ohms with Ohm's law, we find 0.097 amps or 0.33 watts. And then, of course, since we need 2 contactors to charge the battery, we are looking at 0.7 watts lost in operating the contactors at a reduced voltage. Now, perhaps we could do even better. The contactors, the main contactors in an electric vehicle are very large and heavy duty. That they have to be able to carry over 200 amps from the battery to the motor. Now, since our solar charger doesn't really produce any more than 1 amp of current, perhaps we could use a smaller contactor that might require less power to operate. And as it turns out, the Chevy Volt has a set of smaller contactors built into its battery box that are used specifically for charging the battery. And these contactors we found have similar voltage requirements as the main contactors, 12 volts nominal, but in practice they can operate at much less. So here we could supply them with 3.4 volts. We found that the resistance of these smaller contactors was 107 ohms. So then we calculate that out. It required 0.32 amps or 0.1 watts per contactor. So then if we had 2 of those contactors, it would require 0.2 watts. The Chevy Volt's battery box circuitry is somewhat more complicated, and to charge the battery pack on the Chevy Volt, you actually have to operate 3 small contactors. So we would be looking at 0.3 watts there. So here is a comparison table of the amount of energy lost. So here we can see that if we were to supply a full 13.8 volts to the contactors to charge the battery, we could lose possibly 5 to 10% of our solar energy we've collected, which that is a lot, and we should try to do better than that, and we can do better than that. If we were to use diodes, then we would lose like only a tenth of that, at a little less than 0.5%. If we are able to reduce the voltage to our contactors, we can cut that about in half again to about 0.25%. And that's amazing that simply reducing the voltage applied to the contactors can save so much power. And then if we use smaller auxiliary contactors, then that will cut our power losses again in half, down to 0.13%. So about 0.1% of loss or so we can do for charging the electric vehicle battery pack without compromising safety. And of course, because we are dealing with possibly 400 volts DC, safety is very important here, where we want to contain the high voltage to areas that we know where it is, and that are relatively inaccessible to people. And anything using contactors is probably as safe as can be, or so, because that is how the electric vehicle manufacturers do it themselves. Now the thing is, like on the Chevy Volt, we don't think that they are reducing the voltage applied to the contactors. And the reason to not do that would be that when the vehicle is driving, you don't want to risk going over a bump and having the contactors open unexpectedly. So for that reason, when the vehicle's driving, they may always want to apply full voltage to the contactors to make sure that they don't open unexpectedly. So for using reduced voltage supplied to the contactors, we would want to make sure that we only supply the reduced voltage to them when the vehicle is parked. In that case, the chances of any impact that could cause the contactors to open is greatly reduced. We think that the diode solution is safe, but the thing is about diodes is that we have seen diodes fail shorted. And if the diode were to fail shorted, then the high voltage would be allowed to exit the battery box. Now, though, we think that when the diode does fail shorted, that is usually due to overcurrent. So if we have fuses there, and of course the current limited source, then the chances of those diodes failing should be fairly low. So another consideration is, or a typical electric vehicle, the battery box is mounted underneath the vehicle, and it's also quite heavy. So a good solution should not require the battery box to be removed and modified for any reason. So, making any special connections inside the battery box with diodes or adding extra contactors would not be desirable. So the Chevy Volt already has auxiliary contactors in the battery box that we can use for this purpose. So that is great. Now, for other vehicles, like the Ford Energy or the Prius or so, if the battery is more so in the trunk than underneath the vehicle, it would be a lot easier to access the battery and doing the diode method may be a very reasonable solution to do. A future consideration or so would be a vehicle to load the system, or so that, if you may want to use the energy stored in your vehicle's battery to operate devices in your house or something. So, of course, the diode solution won't work with that because we have specifically installed those diodes to prevent power from exiting the battery box. And then the reduced power using the smaller contactors is probably not as big of a deal as it might appear or so, because at over 300 volts DC, that a 15 amp circuit or so is able to supply over 5,000 watts. So that is a good amount of power, and it's probably not necessary to look into other solutions just to get more power on the vehicle to load circuit. But that is also another video. But don't go away just yet. We've got some great news. The converter boards are now available for purchase. So this board is designed to interface to a 72-cell solar array, and that corresponds to a maximum power point voltage of between 31 and 45 volts. And it might also work with the 60-cell solar array, but we haven't tested that. And there's a chance that it may not be able to quite hit the maximum power point voltage for one of those panels all the time. The high voltage output is designed for the range of a typical electric vehicle, between 300 and 400 volts DC. The voltage is regulated and programmable. The power output is about 300 watts. Very conservative rating too, that we wanted to be able to handle the typical power level without needing forced air cooling. It has a lower powered 12 volt charger output for charging the vehicle's 12 volt battery. That should extend the life of it greatly, as well as supplying the power for the contactors and stuff, and battery management system. It has the ability to control 5 contactors independently with 12 volt output, and 3 of those outputs are able to supply a reduced voltage between 0 and 5 volts. As we have just discussed in today's lesson, that will save a lot of power. It has some additional 12 volt switched outputs and 7 12 volt inputs for monitoring other vehicle systems. So that could be used for like detecting the state of the contactors commanded from the vehicle itself. And then the other outputs are so like on the Chevy Volt, like we need an additional output or so, not for contactors, that is a communications enable line that will enable the data from the battery management system to be sent over the CAN bus. It has 2 CAN bus interfaces for receiving data from your vehicle's battery management system or operating as a CAN bridge. It has a switched power, 12 volt power to a fan connector, even though we are intending to not need a fan. We have put the fan connector on there, and it could also be used as a general purpose input or output as well. Now, one of the few things that we can guarantee about this board is that you will need to reprogram it, as the product's still in a fairly early stage of development, and the programmer is built onto the board, so all you need to do is connect to it with the micro USB cable. And particularly since we're dealing with power electronics here, the programming connection is isolated. So there won't be any risk of ground loops or electric shock to your computer for when programming it. The connection to the contactors is done through a removable interface board. So this board will allow all of the vehicle's contactor connections and stuff to be connected to a single cable. And the goal is so that then this interface cable can be unplugged from the board and connected to an additional board we call a bypass board to enable all the signals from the vehicle's contactors to pass through the bypass board and back to the vehicle, so that this converter board can be removed for servicing or in case that it fails. And as we said, we don't want the vehicle's contactors to open unexpectedly. So in order to ensure a very reliable connection for the vehicle's contactors, this interface board also has holes to insert diodes on it. So that way the signals to the contactors from the vehicle's own circuits can go through the diodes on this board and not be reliant on the 40-pin connection here. And that is just an additional benefit to try to make this setup as reliable as possible. Where, like we are, even like during development or so, like we have been using our vehicle as a daily driver. So, reliability is a very important consideration here. And since, we want you to be able to use your solar electric vehicle as well. Now, what we recommend that, only the most experienced and bravest hobbyists buy this product right now. Like we said, it's still at an early stage of development, and as far as like controlling the vehicle's contactors, we'll be making some more videos later showing the process of reverse engineering the operation of the vehicle's contactors. And that is one of the purposes of the 12 volt input sensing lines on here, to be able to monitor the vehicle's contactor operation and to ensure that we don't get the vehicle into an unsafe state by trying to operate the contactors from two separate systems at the same time. So if you want to use this board with a Chevy Volt, you probably should wait a little while for us to write the software and documentation for using the contactors on the Chevy Volt, as well as there will be an additional harness for connecting to the Chevy Volt's contactors that is not available yet. So the ideal customer right now would be either with a home converted electric vehicle that has easy access to the high voltage battery, or perhaps something like a Ford Energy with the battery in the trunk that is easy to access. As last week's Facebook outages have proven, it's not a good idea to rely on a single platform. So if you are even slightly interested, consider connecting to us by another platform, such as Telegram, where we have our Real Solar Cars page, or our GitHub, where we keep the documentation and software for our circuit boards. But we are also maintaining email and postal mail lists So when we have new products or so, we will keep you informed of that. Thanks. These planes.